Welcome to the Cosmic Pie Podcast, Episode 11, Season 4. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
Robert, I'm not by myself today.
You are not by yourself.
You're here.
Actually,
you made it back.
you weren't there by yourself last week. I just wasn't in the studio or anything. I was watching in. I was tuned in.
He was checking up on me, make
Yeah,
sure I did
man.
everything correctly.
And you didn't. We've got a checklist.
To at least
not
get
really.
50%, isn't that a pass?
No, it was a good show.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks.
Here in Grand Forks.
And Robert,
Yeah.
happy St. Patrick's Day.
Happy St. Patrick's Day. Hey, we both got our green on.
And we have the luck of the Irish. We'll have a good podcast today.
That's the hope. Yeah.
You want to do this?
Woo!
You want to do a disclaimer?
Okay. Since I wasn't here
No
last week.
four-leaf clovers allowed.
No four-leaf clovers allowed. But anyway, the opinions and statements made by Wayne or myself are those of ourselves. They are not the opinions or beliefs of the University of North Dakota, the Department of Physics and Astrophysics, College of Arts and Sciences, or anybody else. You just come at us.
And
So-
if you like this podcast,
Like and subscribe. Come on.
please give us that thumbs up.
Absolutely.
We die for thumbs up.
I don't know about that, but
It's surely nice to get one.
it is nice to get them. You know, it's nice to see the views tick up. And the
It's like
likes
back
tick
in the
up.
Roman Empire days, we always look for the thumbs
Yeah.
up. You never want the thumbs
You
down.
never want the thumbs down.
That's a bad thing.
Mm-hmm.
Now, for those of you who like to watch us on Spotify, we do upload our podcasts when we get them, which is the next day, and we do put them up on Spotify, so you do have that option as well. Now, yesterday was the 100th year anniversary of,
Liquid rocketry, or modern rocketry.
liquid rock. So the first liquid-fueled rocket was launched 100 years ago yesterday on March 16th,
Yeah.
1926, by Robert Goddard.
Mm-hmm.
You're going to say something. Go ahead.
I was just going to note that that statement alone is a change because when I was a little nipper, we always were taught and heard that Robert Goddard was the first to make a rocket, which we now know historically is completely inaccurate. But he is the first to use liquid fuel motor to get it up.
Yeah, so the rocket, which you see in its full glory on the left panel with, if you like, the sporting structure, which today, of course, be the launch pad, as we name, and you can see the rocket by itself sort of on the panel on the right, where he's holding it. So it lasted the flight for about 2.5 seconds, he estimated. Traveled, I think it was like 40-some feet.
Oh, I didn't
But-
realize it was that short.
Yeah, it's like the Wright brothers.
Okay, fair
Sort
enough.
of rocketry, liquid rocketry, right?
Right.
Of course, rocket's been around for hundreds and hundreds and hundreds and hundreds of years before that.
Right.
If you think of the fireworks that were done by the Chinese, and how many years ago was that?
And they did use them as weapons.
Yeah, for
So-
sure. So they've been around for a long time. In fact, think of the American national anthem, the rocket's red glare. So the Revolutionary War.
Right?
So rockets were obviously being used back then as well in the 1700s.
They were just solid fuel
They're
rockets.
just solid fuel, not liquid fuel. And this particular rocket, in terms of the propellant, it used gasoline for the fuel and
Oh.
liquid oxygen for the oxidizer, the oxygen source. And it operates a little weird in the sense of how our present-day rockets are designed, starting with, if you like, during the Second World War with the V-2 rocket from Germany. And you can see in the images there, the tanks are down below,
Okay.
and the gasoline and the liquid oxygen are pumped upwards to the combustion chamber, which is near the top. And you can see that cone-like structure, the nozzle of the rocket. So the flames would have came from the top and directed downwards, and there's actually a nose cone that's sort of in the lower part of the rocket itself to
Yeah.
keep the flames from hitting directly on the fuel tank and the oxidizer tank. So it's just a different design than what we're kind of used to.
Yeah.
Nowadays, the combustion chamber and everything is below the rocket
Right.
rather than being at the top.
That's
But-
kind of where I would prefer it to be.
Yeah, but obviously it was just the first kind of design,
Yeah.
proof of concept type of thing.
Yeah.
But it's interesting to know that these experiments by Robert Goddard, professor of physics, were being done in Auburn, Massachusetts, and even in the time in which this was done in the early 1900s, you can see like people living in that area. and they weren't too happy with the experiments that he was performing. And so that gave some pressure to him to relocate his experiments, and eventually he decided to go to New Mexico, where there was no one around for him to bother or them to bother him.
Yeah, I'm imagining if it was gasoline and oxygen, that when that thing came down, I doubt it was a complete burn, which means fire went everywhere.
Well, the thing is, these rockets got larger and larger and larger as he was experimenting. In fact, he was kind of doing what the Germans were doing with, like I said, the von Braun and all the famous people at Peenemünde were experimenting around with the liquid-fueled rockets. In fact, after the war was over, unfortunately, Robert Goddard passed away in 1945 from throat cancer. And so he never met Werner von Braun after the war. But von Braun is famous of saying that when he got to the United States and examined the rocketry stuff that Goddard was doing, that he had the same ideas, that they were the same, even though they never communicated. Because the laws of physics are the laws of physics.
Are the laws of physics, right.
And so it was interesting. He had all the makings, of putting together V2-like rockets and eventually Saturn V and going to the moon than what the von Braun, his team had in Germany
Right.
at the time.
It's just another of those cases that, it's amazing where we would be and what we would have been doing if a life hadn't been cut short, So,
Yeah, I mean, you see that a lot, right? That
Right.
type of speculation. So, but it is what it is, as the famous saying nowadays.
Right?
So what are you going to do?
What
Right?
are you going to do?
Now, comets are back in the news.
Woohoo!
But it's not the comet you might think of, which was mentioned even last podcast, the 3I Atlas. This is a new comet, Robert.
Okay.
So this new comet is, if it's screaming towards the sun, and in the slide that you see here, you actually see the path or trajectory. The bottom part of the path is the first part of April, where it's inbound towards the sun. It's going to make the closest approach to the sun on April the 4th, what we call the perihelion, and then it's going to go around the sun, and assuming it doesn't break up. And that happens
is
a lot to
big
comets.
assumption with it getting that close to the sun.
That's it. So that might be
Wow.
the end of the comet at that point.
Yeah.
But if it does manage to survive and goes back away from the sun, and getting away from the sun then, from our point of view here on Earth, allows us to get hopefully a chance to view it, it should be extremely bright.
Right.
In fact, you're looking at values, for those who are into astronomy and know these units, of about -5 in apparent magnitude, which makes it getting close to the, not quite, probably a quarter moon brightness.
Right.
So it gets it to like the brightest sort of that Venus would get to. It's kind of near those type of numbers. So it should be extremely bright. In fact, it should be viewable then in the sky just after sunset. And so this is after April 4th. And so what we see here is a projection of what it may look like in the sky. So notice April the 8th, that it's high enough above the western sky that you should be able to see it. Notice that Venus is very close to the position of the comet over several nights. And Venus you can actually see as soon as the sun sets and it gets starting to get a little dark in the west. Look for a really bright light low in the western horizon. And that's the planet Venus.
Mm-hmm.
I mean, I saw it like last night, for example. It's easy to see.
Yeah.
And so you can use that as a guide. Where do I got to look for this comet relative to the position of Venus? And you see, you would look for it basically to the left of Venus.
Mm-hmm.
And you'll see that as the days go by, so we go from April the 8th upwards to April the 14th, the comet will be higher and higher in the sky and therefore easier and easier to see. But of course, we'd expect its brightness to decrease. So it's going
as
to
it
get
gets
fainter
further
and
away.
fainter.
Yeah.
Yeah, so we might
Further away
have,
from the sun, I should say.
yeah, so depending on how things work out, that is survivability here,
Yeah.
that we might have a really bright comet to be seen in sort of the dusk.
I mean, this should be bright enough that the tail will be
Oh,
visible.
it's going to be fantastic. But I always get amped up over this stuff, and then, comet predictions are notoriously incorrect.
Yeah.
I mean,
And I'm going to go back to the previous slide for a little bit, because that little inner white circle in the center, folks, that's the sun. So this comet is going to start April 4th, well away from the sun, but it's going to be moving so fast and get so close to the sun that it whips around and comes back almost as far out on the same day. This thing's going to be moving fast. It's going to get really close to the sun. It's going to experience a lot of tidal forces. I'm predicting this thing will break up.
And the comets are not held together like diamonds.
Right.
So they're notoriously to be think of it as a dirty snowball. Is one description that Fred Whipple used many decades ago.
Right.
In some sense, that is correct. And of course, there's variation in the intrinsic properties of the comets. They're not all exactly the same. And so we'll see what and the other thing is, in this view, you can't tell how close to the sun it's actually getting because it's a two-dimensional
It's a two-dimensional projection of a three-dimensional
space.
Yeah.
So you don't have that to guide you. But hopefully it stays together for our benefit.
Yeah. I would love to see a comet that bright.
It's not going to hit the Earth or anything like that. It's just
Right.
going to give us a nice show if it survives closest passage to the sun itself.
Right. So here's hoping. Keep your fingers crossed.
Here's hoping. And here's another thing to hope for. And this is attention now going back to the planet Venus. Now, there's a little bit of history here, and in particular what we're looking at is Russia's desire to return to Venus. They have done a lot of work, and we'll give them credit for a lot of work in the past. In fact, the only spacecraft that have, and there have been a couple of them, the only spacecraft that have ever landed on the surface of Venus have been those produced by the Soviet Union.
Right.
So they have, like I said, a history in this. And so they are planning, and of course plans, things can change, but they are planning on sending a spacecraft to Venus in 2036, so in about a decade from now.
Okay.
Now, to be fair, the space program, the space industry in Russia is not the same as it was back in the 1970s or in the 1980s even. It's been degraded a lot due to various things, including the breakup of the Soviet Union and also wars and things like that, which drain money from the treasury. And that's the case, that we see that in no matter who's involved in wars. It always costs money.
Yep.
Blood and treasure, that's what it costs, right? Whether you like that or not, it's the case. So we'll see how this affects everything. But right now the plan is to not just go there and land like they've done in the past, but actually to have basically three main components to this mission. The Venera mission, I should say. In this case, it's Venera-D. These were the name of the landers which landed in Venus in the past. Venera, 10 and 11?
Something like that.
These kind of things.
I mean, there were only like 3 of them that actually made it to the surface, right?
And survived for a while.
Right.
They typically survive for about an hour or so.
Right.
And just to remind people, the pressure on the surface of Venus is like roughly 80 times Earth's pressure.
Right.
And it's extremely hot.
Hot enough to melt lead.
And hot enough to cook a pepperoni 16-inch pizza in about 10 minutes.
Right.
Those kind of conditions.
And then there's the nitric acid and the
Sulfuric acid atmosphere. So it's very corrosive. It does wonders to electronic components.
Yeah.
And in fact, people have been designing these for sort of flexible, heat-resistant, acid-resistant electronic components here on Earth. And the idea is that maybe we can put them in a future spacecraft that will go to Venus.
Right.
So that's why we kind of don't bother too much with Venus. We go right to Mars.
Yeah. A lot of work, I know, because I had colleagues at Case Western Reserve working on this very thing at Ames, I believe it is. And they were experimenting with ceramics, liquid cooling, different metals to do the soldering of the electronics and things like that.
And to be fair, I mean, the United States is planning to launch the Da Vinci mission to go to Venus and explore. And we've sent the Venus, a Pioneer Venus spacecraft in the past.
Right.
So we've had also, and the Mariner flights that went by and so on. So we've done some exploration of Venus. And we had the Magellan spacecraft that went in orbit around Venus and used radar to map its surface to
And that's still the best surface maps we
high
have.
resolution, yeah.
Yeah.
So we have all that. So we have, it's not like Venus was left alone totally by the United States, but
Right.
Russia's back in the game. So what are they planning on doing? Well, they're going to launch a vehicle that include an orbiter. So you can see some of the mass constraints they're thinking of right now.
Now, these are tiny.
These are tiny. So we're looking, I mean, they're a smaller rocket and it's cheaper to make. And
Right.
microelectronics nowadays. And so you don't need the big, huge,
Fair.
thousands and thousands of, kilograms of equipment now. So an orbiter, somewhere they're thinking between 40 and 50 kilograms. A lander,
So folks, that's for our American audience, that's about 120 pounds.
120 pounds. So that was designed to go in orbit around the planet and do different measurements. Then there's a lander component, which is sort of the most exciting part for me.
Yes.
And that's somewhere, they estimate 10 to 15 kilograms in mass, and the science payload on the order of 4.5 kilograms, which I'm sure will include a camera,
Why wouldn't it?
because that's one of the amazing things. You can go online and look up photos taken from the surface of Venus to get an idea of what it looks like. And that's very interesting and captures your imagination, wondering what it's like if you could roam around on the surface. The other interesting thing about Venus, of course, is that it has about the same mass of the Earth and about the same size of the Earth. But other than that, they seem to be completely different.
Completely different. There's no major magnetic field around Venus.
No plate tectonics.
No plate tectonics.
They need a very high pressure and a very inhospitable atmosphere, as we mentioned already. Even though it's a little closer to the sun than we are, that does not make up for the huge temperature on its surface.
Right.
That's mostly due to the fact carbon dioxide laden atmosphere trapping the infrared light of the greenhouse effect.
Right.
So you have what we call a runaway greenhouse effect on the planet itself. And something that scientists use who are worried about what happens eventually to our Earth, what our Earth could turn into, and they always point to Venus, it may turn into a Venus-like planet,
Right.
which would not be good for
No.
life on the Earth.
That would be inhospitable.
For sure. And then the third component of this vehicle would be a balloon. And that has been proposed many years ago. In fact, that's part of what we're seeing, recent proposals to NASA to go back to Venus for the United States. In this case, the Russian balloon would weigh somewhere around, would have a mass somewhere around 20 kilograms, and it would be designed to float in the upper atmosphere for about 5 days at least. That's sort of the minimum number. And the winds on Venus, the upper atmospheric winds, are huge.
Are huge.
Right?
Yeah.
So it could be, in 5 days, they could be whipping around a lot.
Right.
It's going to cover a lot of distance. But that way you get direct in situ, if you like, measurements or tasting the atmosphere, right?
Right.
To taste the atmosphere, you can tell its composition directly.
And I was about to say, and what is the importance of that? We can sit here and tell how much water may have once been present because of the residuals, how much the sulfuric acid is really playing a role, all kinds of good information.
And the height of the balloon will change, so you get like profiles, density profiles, how the density changes depending on the height from the surface of Venus, the particle,
particulates,
sizes,
yeah.
the composition. There's even speculation that depending you're on a certain layer in the atmosphere of Venus is actually a good place for life to exist. The pressures are a lot less. The atmosphere is not as as dangerous, if you
It's
like.
caustic.
Yeah, so maybe life form there, like little flying jellyfish that are floating around on the global jet stream of Venus, the Venusian jet stream.
Yeah.
These kind of ideas. People have speculated about this for decades, but how do you know for sure unless you go there to make direct measurements? So,
Right. Well, and the answer is we have ways, but they're all indirect methods. You still like having a physical sample, so.
And the other thing you always wonder about in the future, and I'm sure it will happen if you go far enough into the future, in the future will we ever get to the point where humans will be walking on the surface of Venus? So you have to mitigate the pressure.
Have to mitigate the pressure
You have
and
to
the temperature.
mitigate the hostile, corrosive nature of the
I
atmosphere.
really don't think you'll have people walking around, but you might have a rover
In the
type
future,
situation.
given infinite amount
Okay.
of time,
Okay.
it's going to happen. But of course, first, we're going to have rovers on the surface.
Absolutely.
Now, can you build a rover that would survive?
And that's the research James
condition.
is doing and so forth. Yeah.
And that would be great because imagine having a rover like we have on Mars.
Mm-hmm.
In this case, you're sampling the soil and the
Right.
rocks and doing detailed, direct analysis of this material. You're going to find a lot of interesting things, I'm sure.
I agree.
So I can't wait for that to happen. But the way things are going, I don't know.
I don't know when it'll happen, but
That's the other thing, right? You might have to wait for a while.
but we also have the explorer mentality. Just finding out is important enough to warrant it. So we'll see if that type of thinking.
For this planet, we got to do a lot of prep work. You just
Right.
can't take a rover we designed for Mars and put it on the surface of Venus. It won't last very long.
Yeah, I doubt it'll hit that hour mark of.
Even if it was nuclear powered, right?
Right.
You'd have to survive the pressure and the corrosives. You have to make it of a material that's not going to be destroyed by the acid-laden atmosphere and can survive those huge pressures. So everything's completely different in terms of its design. And you probably want it nuclear powered, just like we have on Mars.
Right.
Because the atmosphere is so thick. What is the sun level at the surface?
It's pretty dim.
It's pretty dim.
The Russian photographs.
Yeah. So you're not going to be able to rely on solar panels for sure. Oh well.
All right. Next.
Now, speaking about rocketry, and we opened, of course, commemorating the 100 years since the invention of the liquid-fueled rocket and flight of the liquid-fueled rocket, we have an update here on the Artemis II mission. So this is sort of new information. It just came out today that the rollout back to the launch pad will take place this Friday, March the 20th. And that still puts NASA in line for the first launch attempt on April Fool's Day.
I wonder if somebody thought about that.
April the 1st. And I pity the fool that doesn't turn on the TV and watch the launch. Can I
Right.
say that on that day?
I guess you can.
Mr. T.
Yeah.
Anyways, so the rocket itself, as far as they're telling us, all of the problems, the major problems have been fixed.
Uh-huh.
The problem that caused them to roll the rocket back to the vehicle assembly building has been fixed.
Okay.
It was a filter that got squeezed out of its groove, essentially,
Okay.
and pushed and restricted the flow of helium into the upper stage. That has been redesigned in some sense, so that's supposed to be all fixed. The problems they're having with the leaking of the hydrogen and so on, all of those issues have been fixed, as far as we know. And they're confident enough that they're not going, once they get the rocket back on the launch pad, they're not going to do one of those wet dress rehearsals, which means you fill up the fuel and fill up the liquid oxygen into the rocket and see if everything, there's no leaks and everything's working fine.
Right.
They are confident that they don't have to do that. And that's why the launch attempt will be made hopefully on April the 1st or very close to that.
Cool.
If you don't make it in the first week of April or so, I think then you have to wait sort of the end of April and then you're into May.
Yeah.
So, I mean, they're really focused on trying to make the April 1st launch. So we'll see what happens. The other interesting thing that's been going on is the upper stage. This upper stage is not designed to support a landing on the moon itself.
Okay.
They were supposed to put a different type of upper stage on there. In fact, they built a whole new crawler transport system to take them to the launch pad with this extra height, this change in the configuration. And now they don't need it, and it's almost completed. I mean, there's some weird things going on there. And that's because, recall that a few weeks back, the Artemis program had a major shakeup in terms of what it plans to do. So instead of landing on the moon in Artemis III, so Artemis II, the one that's going to be launched this April, hopefully, that's designed to send up 4 astronauts to go around the moon and then come right back. So that wasn't even designed to go in orbit around the moon, let alone land on the surface. Artemis III was going to be the first attempt at landing on the moon
Right.
in this era, modern era. But that has now been changed. So they're going to use Artemis III to test the landing craft, one or both of them. One is being produced by Blue Origin, the other one by SpaceX.
Okay.
Whether or not they will be ready, one or both, for Artemis III, that's something else. In fact, if neither of them are ready, Artemis III just gets delayed because its sole purpose is to test out at least one of the
Test the
landers
landers.
in orbit of the Earth. So where you're nearby in case something happens. And they did the same thing way back on Apollo 9, if you look in the history of the Apollo program. So that's nothing new. We're kind of repeating that strategy here. And so that means that there's going to be an attempt at landing on the moon then for Artemis 4 and 5.
Okay.
And then the whole program will be canceled or something. Or
Right,
who knows, I
right.
mean, it's extremely expensive. Each of these rockets costs north of $3 billion. And the way it's in the past has been going, it takes several years to launch these rockets, everything ready to go. That's just not, it's too expensive and it's not enough.
Yeah.
So they're hoping that with the hiring of a lot more people, that they'll be able to launch the rockets a lot sooner, maybe several times a year if they can. Maybe that'll drive down the cost of the rocket, but If you ask us, I mean, we've had this discussion with various people, including Dr. Space a couple podcasts ago. It doesn't seem sustainable.
Right.
And if you really want to go back with a human presence on the moon to stay, to build a permanent base on the moon and then go on to Mars, it's going to take a different type of system, a transportation system to do this.
Yeah.
So
This really just doesn't seem the way.
No, it doesn't. It seems like
So-
you were just repeating past history.
Right.
Nothing
So-
new or novel in that sense.
You know, I mean, yeah, I would like to see more about the habitation, because you're on point. We've been to the moon. We can do that. It may take us a little bit to refigure out how to do it, but we've done it. We can do it again. But staying on the moon, I want to hear more about the habitation modules and things like that they have in mind.
And the thing too about that, if you show us the development of the actual lunar base, Moon Base Alpha for those Space 1999 fans, a Moon Base Alpha, in some sense, couldn't you use a lot of those designs again for something on Mars itself? Maybe.
Maybe.
At least as a starting point.
Right.
And just do the modifications to support a Martian environment rather than a lunar environment.
Yep.
And as we talked about in the past, it takes a long time to get to Mars. That's one of the problems.
What,
if
5,
you're-
6 months there?
Yeah,
at
typically
best?
6 months there, and you're looking, and you have to wait a while to return. You have to wait like a year and a half or something for the alignment of Earth and Mars to be such that you can spend another roughly 6 months getting back.
Right.
So you're on Mars for a long period of time. You're not 3 days away like you are on the moon.
Right.
And therefore, as anything goes wrong, you're in
It's just wrong.
you're in big. You could
Figure
be,
it out.
You could be in big trouble. So if someone needs open heart surgery on
Yeah.
Mars, you're going to have to do it on Mars.
Right.
You're not going to be able to send that patient back to Earth, probably. So there's a lot of issues that, and in fact, you sign up for it.
Yeah.
In fact, the other thing too is that you want to pick young people because presumably they'd have less of a medical issue.
Presumably.
But then there's another thing you worry about in terms of the human body, and that's exposure to radiation, both from the sun and cosmic rays that originate outside of our solar system.
Yeah.
And this radiation can damage the cells. So there was talk a long time ago that, well, let's not put young people in space, let's put up older people. So by the time that they're exposed to this radiation and maybe develop cancer as a result of it, well, they're going to be in their 80s and 90s, so does it really matter? But if you send up a 30-year-old, they're going to be in like early 50s when they develop this cancer. They still presumably have a lot of decades left to live,
Right.
to enjoy. So you can make that type of argument as well. But then you go the other argument, well, then body parts start wearing out when you get older.
Right.
So are you more, the possibility of a heart attack or a stroke, is that greater when you're in your 80s compared to when you're in your 30s, you see?
There you go.
So you have
Both
those
solid
considerations.
arguments, but which
Now-
one do you go with?
And the radiation argument is actually quite important. In fact, there is a whole part of NASA that's watching the space weather, even for Artemis II launch. And they're taking all the information they can, including observations on the other side of the sun right now from Mars, from our rovers,
Right.
where the alignment of Mars is such we can see the other side of the sun that we can't see presently from the Earth. And they're looking for the development of large sunspot complexes. And when you have those on the surface of the sun, and we can resolve those from the rover cameras on Mars, that could signify an enhanced activity of solar flares.
Right.
And therefore, they could alert us to say, hey, maybe we should skip and wait till next month to launch,
Yeah.
where the chance of a major solar flare happening while they're on their way to the moon or coming back, I mean, they could be in a lot of danger.
Yes. And folks, let me point out a little point. We keep hearing about the Earth's magnetic field being our shield. This is true, and it is the major component of our shielding, but we've also got 90 kilometers of atmosphere that de-energizes these incoming particles. Because while the atmosphere is pretty thin, it's thick enough that after over 90 kilometers, it takes a lot of the juice out of these particles.
And the other thing is, if you're in the Artemis II Orion space capsule, I mean, it's going to go around the moon, but not hug the moon.
Right.
It's pretty far out. It's outside the protection of the Earth's
Of either the atmosphere or the
magnetic field. So it's going to be, it's a sitting duck in a sense. So we want to make sure that we launch at a time when the space weather is relatively quiet and
Yes.
less of a probability of getting, exposed to these high energy particles.
Right.
So,
I mean, that really is one of the big things about space travel. People aren't kidding. There's a lot of danger from radiation exposure.
and then, of course, if you broaden that out to say, okay, what about the 6 months going to Mars? Well, that's when you have to do things like maybe the water that you carry with you. You have the crew compartment set up such that you can use that water as a shield, as a
Right.
blocker, an insulator to absorb a lot of those high energy particles
Yeah.
that we would get from the sun. The problem is, of course, cosmic rays would come in on any different direction.
Yep.
So what do you do in that case?
And the best thing I've seen is you put that water that you're talking about around a sphere that has a doorway through it, and then the flap of the water can close up over the door.
Yeah.
Because, water, one, has a high cross section, which we measure in, believe it or not, barns, as in hitting the broad side of. And it also has the capacity to absorb a lot of neutrons, which are the real danger.
Yeah.
So water is a very effective shield.
And that's why there's a lot of emphasis. In fact, there should be even more on some of these plasma rockets that people are trying to develop at NASA and otherwhere.
Right.
And what they would give you is and even nuclear rockets, they would give you the ability to get to Mars a lot quicker. So instead of spending 6 months in interplanetary space between Earth and Mars, you'd only spend maybe 1 or 2 months.
They also give you the ability to have a high enough thrust that you don't have to wait till that perfect window, that Hoffman transfer orbit, to do the trip. You can actually launch at it almost any time.
And then once you do arrive on either the moon or Mars, then you got to worry about what happens if you're on the surface and something is coming. So you got to get underground.
Dig in.
So it's like the Marines landing somewhere. You had to dig a foxhole as soon as
Right.
you hit the ground running type of thing. Just you never know when that can happen, right? So
Right.
you have to be prepared. So these are some of these, a huge number of considerations that people will have to look at, of course, when we get to that point.
And this is why some of the biggest astronomical research is actually looking at the sun because of space weather.
And this is, this gives us an idea then of Artemis II. If something happened, in this case, what is the protection? So here's sort of a cutaway diagram of the spacecraft itself. There's really no shielding here that you can use.
Oh, no, there is not, is there?
No, there
Wow.
not. And so we really, really have to worry about it at least for the early Artemis flights. And so one of the things you're going to do, the astronauts, they're going to carry monitors to keep an eye on the radiation environment.
Okay.
So at least to be able to tell you, oh, Robert, by the way, you've absorbed enough radiation on this flight that you would accumulate naturally, taking x-rays once in a while at the dentist and so on for the next 80 years of your life, right? Sorry about that.
It's 2 days back, right?
You did volunteer, right, Robert?
Oh, man. Oh, dang.
Oh, well, anyways. How old are you, Robert? You don't have to worry about cancer. Something else will get you before you...
Right?
Anyways, but so some of these spacecraft then will have to be designed for that type of protection.
Yeah.
Definitely. There's no way around
and any
that.
of the habitations will have to be, and all sorts of things.
Yeah, just one
It's-
more
it's
thing you have
an-
to consider.
It's a nifty engineering and science problem that needs to be worked out.
Yeah. Now, besides our own sun, which occasionally produce a lot of radiation, you wonder, well, what about other stars that are out there?
Mm-hmm.
And in a distant future, hopefully, humans will travel to other star systems and study those planets.
Okay.
And so we wonder then about suns that are like our own. And this is a recent study that was done using Gaia data. So Gaia is this spacecraft that it's finished observing now. It finished a little over a year ago, January of 25. And they're still processing the data, so we're still getting the releases of the data over time. It's not finished yet. And what it was designed to do is do very accurate measurements of the location of stars. And from that, use what we call parallax to try to get an estimate of how far away these stars are.
Right.
So parallax, a good way of thinking about it is imagine yet you have your finger in front of your nose and just put it a few inches in front, and then look at your finger with one eye and notice where it is in the background, and then look at it with the other eye and notice where it is located in the background. And then kind of switch back and forth if you can do that, and you see that shifting effect. And that shift is caused by the fact that you're viewing it from two different locations, and the shift that you actually see is determined by the separation of your two eyes and how far away that finger is from your nose, if you like.
The further away it is, the left shift. The further apart your eyes, the more shift.
Yeah, so you can repeat that experiment by just taking your finger and putting as far away as you can from your nose, and then looking at it with one eye and then the other eye. Notice how it shifts relative to the background. You'll notice that shift is a lot smaller than when the finger was closer. And that's essentially what we do in astronomy. We look at the stars from different locations and use that shift, what we call parallax, to get an estimate of the distance to that star. And so this spacecraft, which is above the blurring effect of Earth's atmosphere, its main purpose was to do just that, was to look at these shifts to try to measure the distance to as large number of stars as it could.
And it did something like 1 million stars?
Oh, billions of stars.
Okay.
Right? Over 1 billion.
Okay.
Yeah. And so it's like the best sort of measurements we have of the direct distance using this technique.
Because this is geometry. Either geometry works, only on Earth, or it works everywhere.
And it works. That's why we have Pi Day this month. You
Right.
see, 3.14. In fact, we build things. So obviously geometry must work. We know how to slope your roof just right and so on and so forth.
Yeah.
So obviously we know the geometry.
There you go. So, things are really that far away, folks. The geometry, geometry only works here on Earth.
Now, the current release of data that's available publicly from the Gaia mission is this data release number 3, DR3. And here's a recent paper that's using DR3 to search for stars which are like our sun, solar twins, as they call them.
Why is that important?
Well, it's important in a number of ways. Number one, we can look at other stars and see how representative they are of our sun itself. So we don't, for example, in the future, do stars like our sun, do they undergo really high activity every thousands of 10,000 years or so? And if that's the case, if you can look at a large number of these stars, you're going to, chances are, catch one of them in this sort of high activity environment to be able to kind of think about, man, our sun could do that also, to worry about that. And so there are many things that you want to understand. So the way that they selected these solar twins is by 3 different ways. Number one, looking for stars that have similar, what we call effective temperature. So this is a technical term that just means the surface temperature of the star if it radiated like a perfect black body. That's what we mean by the effective temperature.
That doesn't happen.
No. And that's a theoretical object in physics where it would absorb all light that falls upon it, and that's where the black part of the black body word comes from. But then it turns around and re-emits that light over different wavelengths, but there's a peak. The preferred emission is at some well-defined wavelength or frequency given by Wien's law, so we can characterize all of that. And it's a very simple object in a sense in physics, and that's why we like to use them. So they looked at stars then that are similar to our sun in terms of surface temperature, also in terms of surface gravity, which is really a combination of the size of the star and its mass, to have something where the acceleration due to gravity on its surface is similar to what we'd have here for our sun. And they also looked for stars that are similar in terms of composition, what we call metallicity.
Okay.
So what they found were nearly a little over 6,500 stars in the Gaia catalog that were similar to our sun based on these 3 parameters. And that turns out that's actually 30 times larger than any previous catalog that's ever been published.
Right.
So this is a large set of data.
Yeah.
And you wonder, out of that data set, are any of those stars, one or more, did any of those actually form near our sun?
That was my question.
And that would give them the same composition. But of course, those stars could have more mass or less mass than our sun, and they would fall out of the selection
Right.
because of that. So the chances of having a star that's very similar in terms of a temperature and surface gravity and having essentially identical metallicity, so that you could wonder, is it a sister or brother to our sun, is pretty small.
Right.
So chances are that's not the case what we have here.
And I want to point out, because a lot of people will go, well, how do you know what the surface gravity of the star is? And like the answer is like most things in astronomy, it's in the spectroscopy, because different surface gravities are going to broaden or narrow the spectral lines in a predictable fashion. So we know that from laboratory experiments. And we can now look at the spectra and see how broad the lines are, how compressed they are, and say, okay, that means the surface gravity has to be this value.
Yeah, so there's lots of effects. For example, you can detect, whether or not a star has a magnetic field, how strong it is by looking at the spectra. You can determine if a star is rotating and how fast it's rotating by looking at a spectrum.
And again, that's broadening because one side of the line will be broader than the other.
And you can look at turbulence. There's all kinds of information that you can get by just simply analyzing the spectrum of stars.
The light.
And in fact, that's how you really go from astronomy to astrophysics.
Yes.
Is that sort of work?
That is that crossover, yeah.
Now, if we look at the next slide, it's interesting that taking your roughly 6,500 objects and looking at their properties, what we find is that there is a distribution of ages
Oh, wow.
between about 4 and 6 billion years, and our sun is about 4.5 billion years old. So it kind of fits right in the middle of that distribution very nicely.
That is a nice graph, Dan. Wow.
And the other thing that and this particular graph shows is the distribution of how far away these stars are from the center of our Milky Way. So in this particular graph that you see here, figure 2 is labeled. The bottom, or the horizontal axis, is the distance away from the center of the Milky Way in kiloparsecs. Now, just to explain to you what a kiloparsec is, most of the time when we use measurement of distances in astronomy, we use light years, and that's simply the distance that light travels in 1 year. Okay. So in this case, we're using a different unit of length known as a parsec. 1 parsec is equal to 3.26 light years, approximately. And it's defined as using the same parallax technique. How far away does a star need to be from us such that, as observed from Earth on one side of Earth's orbit and 6 months later on the other side of Earth's orbit, it would display a shift, and this shift is half of the total shift, by the way, of exactly 1 arc second. And that distance is 1 parsec, 3.26 light years.
And for reference, there's 3,600 arc seconds in 1 degree.
And for reference,
Yeah.
the distance from the Earth, the average distance from the Earth to the Sun, is known as 1 astronomical unit. And 1 parsecs through our 206,265 AUs.
And that's just because of the geometry.
The geometry.
Yep.
So in this case, the units that we're using in the horizontal, the bottom axis, are thousands of parsecs. The sun is about 8 kiloparsecs from the center of the Milky Way. And notice that the distribution shows that that is near the average that we're seeing for these solar twins. The other thing is that it is expected through modeling of the motion of stars around the galaxy that over the 4 or to 6 billion year lifetime of these solar twins, they've actually migrated outwards from the closer to the center of the Milky Way. In fact, we expect stars like our sun may have traveled up to 10,000 light years from the center, which means when our sun first formed, it may have been at a distance of roughly 16,000 light years from the center, not as its present day distance of about 26,000 light years.
So it's the lower mass stars then are migrating outward?
Yeah.
Okay.
It's amazing.
That's interesting.
Now, what complicates the galactic motion in all of this is the presence of the bar. in our galaxy. Our galaxy is what we call a barred spiral galaxy. Roughly 2/3 of all spirals have at least a little bit of a bar that you can barely see, or a nice prominent, strong bar that you can easily see. So our Milky Way, as far as we know, is a barred spiral galaxy. That has an impact on stellar motion. And so the model of the galaxy you need has to take that into consideration. So there is uncertainty in that.
Right.
But,
Because they would slow down as they hit a bar.
but compositional information goes a long way here. We know that the composition can change depending on where you are in the galaxy itself.
Right.
And so based on the composition of these solar twins, they seem to be consistent with forming closer to the center of the Milky Way, having migrated outwards over time.
That's nifty. That's a neat. Yeah. Need to do some reading.
Now, the next thing we want to pick up is a story about carbon dioxide and its relationship to the moon of
Europa, Jupiter,
Europa. Remember, you can land on any of the other ones,
but not Europa.
and that's from the movie,
2001, Space Odyssey.
yeah, or the second part, 2010.
That's right. It's from the second part. Derp.
Yeah.
I knew that.
So what we have here, so one of the interesting things is we do have a spacecraft. We have actually a couple spacecraft. The JUICE spacecraft from the European Space Agency. It's on its way to Jupiter to study its system of moons and the planet itself. But we also have the Europa Clipper. In fact, in the past, if you look through some of our podcasts, you'll find that Bonnie Doretta was here, and she's one of the chief scientists on the Europa Clipper mission out of JPL, and she talked at length about the mission. So it's going to arrive in the early 2030s at Jupiter, and one of the targets to study in detail, hence its name Europa Clipper, is obviously the moon Europa. Now, Europa and some other moons of the giant planets, like Saturn, for example, it's kind of these areas where they may have formed life in the past. That's the interesting thing about this. In fact, there's been speculation that there is a subsurface ocean in they're essentially like planets, right?
Right.
And objects like Europa, where if you could drill down through the ice, so if you find some kind of a thin spot in the ice and then drill down through there, you find yourself into a salt-like ocean underneath.
Saltwater ocean, yeah.
And maybe life formed there, right? So you have a camera hooked up to a submarine-like probe, unmanned, and it's swimming along in the ocean, and the last thing it sees is this big mouth of some kind of a creature, a squid heading towards it or something.
I don't think that's going to happen, but...
Do you know for sure, Roger?
No,
Do you know for sure?
absolutely not.
Of course not. And so that's speculation, of course, but that's what makes it very interesting, especially from a sci-fi point of view. But then again, it motivates people to want to look, right?
Right.
Is this the case? Number one, does it have an ocean? And we know that from moment of inertia type of measurements. It's
As
like,
well as magnetometer
yeah, it's like
measurements.
taking an egg, right?
Yeah.
If someone passes you an egg, how do you know it's hard-boiled or not?
You spin it,
You can spin it,
right?
and that gives you that information. It spins differently if one is hard-boiled compared to one that's soft. That's not hard-boiled.
And then I mentioned the magnetometer. Thanks to Jupiter having a huge magnetic field, well, we know what effect a layer of salty water would have on the magnetic field around this moon, and that's what we see. So,
Yeah, it's like you don't want to be swimming in a lightning storm in the ocean.
right. Yeah. And that's a big problem, too, for any life that might be there.
So this study is looking for carbon dioxide. Now, we know that carbon dioxide exists on Europa in the past. It's nothing new. But there were studies that suggested that it was concentrated in various cracks and features that you see here on the surface. But this latest study shows that not so fast. It may be more widespread over the surface of the body than what we thought. And these observations are done with the James Webb Space Telescope. Now remember, James Webb is sensitive essentially to mainly infrared wavelengths. And so at the right infrared wavelengths, you can actually look for the signature of carbon dioxide. And that's what you're seeing here in these three images. So on the far left, we have one taken in the infrared at 2.7 micron wavelength, the middle one at 4.2 4.27, and the one on the far right at 4.25. And this patchy like brightness you're seeing here are patches of carbon dioxide on the surface. So you know the carbon dioxide is going to be in ice form. It's not going to be gas.
It's not going to be gas.
No, it's too cold. And to kind of support that, we have other observations. We talked about spectra already. So these observations are with the NIRSPECT, the IFU instrument on board the James Webb Space Telescope, integral field, unit. And so what you're seeing here then is the reflectance spectrum as a function of wavelength. So wavelength is plotted along the horizontal or bottom axis. Units here are microns. Looking at the numbers, all you have to think about is the fact that you're looking in the infrared, given the numbers that you see here.
Right.
And you can see characteristic dips in the spectrum, absorption features, due to the presence of
Carbon dioxide.
carbon dioxide. So that's the proof. That's how we know it's there. Because you could take an image of certain wavelengths and say, okay, it looks bright in the image. How do we know for sure it's not something else? Well, take the spectrum.
Take the spectrum. That's
this-
always what we're looking for.
Yeah. So we know then that carbon dioxide is more spread out over the surface of Europa than what we had thought. What is that in terms of implications for life? Well, we just don't know.
Right.
I mean, we know carbon dioxide is linked to life here on Earth, and
Well,
that's nothing new, but what impact does that mean in terms of life existing on Europa? That's a different thing altogether.
of the elemental impurities in the universe, I mean, the universe is mainly hydrogen and helium. The rest is impurities, but of those impurities, carbon and oxygen are two of the most abundant. So finding carbon monoxide or carbon dioxide somewhere outside of Earth is just, the interesting thing here is that it's widespread instead of focused in particular locations.
Yeah, for whatever reason.
For whatever
we don't
reason.
even understand why that's the case.
Right.
And that'll be part of the study, of course, that Europa Clipper and the JUICE mission will do,
Right.
is to try to figure out why that is the case. Now, speaking about life, very interesting paper that just came out recently in Nature Astronomy is looking in detail of the material that was brought back by the Hayabusa spacecraft, which is a Japanese mission to bring back material from the asteroid Ryugu. And through the analysis, they discovered the presence, essentially, of the building blocks of DNA. How exciting, Robert.
That's pretty exciting.
Now-
I mean, that gets back to all of the building blocks necessary may have been delivered to Earth, an early Earth, from meteorites and asteroids.
And that's not so far out, no pun
Right.
intended, because our own water is thought to have become deposited here on Earth from things from outside,
Yep.
like comets.
Right.
Well, if comets can deposit a huge volume of water on Earth, why couldn't asteroids then deposit different types of material here on Earth
Yep.
that help jumpstart ultimately the formation of life itself? And you know the interesting thing in all of this? We can speculate all we want. You know why? Because nobody has a clue how life first formed on this planet. So we can do anything we want in terms of trying to figure out why this is the case. Where did life ultimately come from?
Right.
What do you need
What do
to
you
make
need?
life on this
The
planet?
components are definitely ubiquitous. I mean, there's no other way to put it. The components are everywhere we look. We're finding amino acids in cold molecular clouds in space.
You know what would have been cool?
What's that?
It would have been cool to live in a solar system that had planets like the Earth, let's say 3 of them spaced out on the same orbit.
Oh, that might be stable.
Would Earth 1, 2, and 3 ever develop life like obviously happened with our planet? In other words, if you have life on one of those 3 Earths, would life naturally have arose on the other two,
two.
having the exact same conditions that we have here?
Well, I would find it hard to believe that it developed in the same pathway, but interesting.
If the basic ingredients like water and maybe, the building blocks for DNA was brought to our Earth from outside, asteroids and comets, one would assume that would also occur on those other 2 Earths. And why we want, well, we could have 2, but let's say 3 of them, just for sake of argument, we're playing a game here. If they're at the same distance from the sun, so I'm trying to make the environment the same, identical, would have life got a foothold on all 3 of those Earths?
And I would say from the evidence we're seeing, probably. You know?
Now,
That's what I'm saying, though. The development pathways may have been different because now we need to bring in tectonics, volcanism, atmospherics.
and with things we talked about in the past, like cryality,
Mm-hmm.
left and right-handedness, well, if they're coming from the same building blocks, they will have the same handedness.
That would be supposed, yeah.
It's just interesting. I mean, we don't live in that type of solar system. We live in a solar system where we have only the one planet that has life as we know. But did life, was it able to get a foothold on another planet like Mars? Because the condition of Mars was very different billions of years ago.
Mm-hmm.
And then because of the changing condition of the planet got wiped out, or at least went
Sorry.
underground to the point where we can't recognize it. I mean, we haven't been there directly.
Right.
And we don't see evidence for it yet. You see what I'm getting at.
Yeah.
So it could have started and then stopped in a whole bunch of other places, or maybe it's still there at some low level activity, at cellular level, even today, underground in Mars, protected from the ultraviolet light from the sun, sort of thing.
Right.
And so who knows, right?
knows?
And there's only one way to find out.
Right.
You know what you got to do.
And again, as I
Call it a
mentioned-
field trip.
Absolutely. Let's go. And it's like, kind of, we do know a lot of how life developed because we know things about bilipid, layers do form naturally. They do close up and form cell-like structures. They do, we know a lot about how the steps involved, but getting them all to happen, that's what we don't know.
So the big story here is the 5 key components that you need for DNA and even RNA,
Yep.
right? The components you need for both of these is found on this asteroid, this material.
Yeah, that's crazy.
And it's not like we picked the one asteroid that has it. We
picked an asteroid at random.
asteroid because we were able to get to it.
Yeah.
So the trajectory was right, but we didn't pick it because it had this stuff, right?
Right.
So if it's on this asteroid, how many other asteroids of tens of thousands that are in our solar system have this type of material?
Yeah, hundreds of thousands. Yeah.
So it's just amazing when you think about it.
Right. And it's all out there. And it's in comets. And it's, yeah.
And if it's in our if it's in our solar system, why not other solar systems?
Yes.
And therefore, for those solar systems that had planets, it was just right in the Goldilocks zone, right?
And
The
liquid
distant-
water and everything else.
Why didn't life develop on those planets? And if intelligent life developed here, why wouldn't it develop there?
I've got some answers for that, but,
It might take a lot. Maybe it only develops one out of every so many millions,
Right.
but there are literally trillions of planets
Bingo.
in our galaxy alone, and there's at least 1 trillion galaxies in the observable universe.
Right.
So there's 1 trillion times 1 trillion planets to pick from. How many advanced forms, not cellular type of bacteria or
Right.
one or multiple,
But-
how much complex life forms have developed on those other planets?
Absolutely.
It makes you wonder for sure.
Oh, yeah.
If you wonder about stuff like that, one of the things you can do, of course, is study higher education.
Yep.
Go to like the University of North Dakota, because here in North Dakota, we have lots of programs, both in science, technology, engineering, arts, and mathematics.
That's it.
And get involved. Get involved
involved.
in some higher learning sort of.
And I will say, before we get too far in our outro, Wonder Goon poses a very nice question. But does this conclusively support panspermia? I would only object to the conclusively. It does support panspermia. Conclusively, we need a bigger sample size than one.
Yeah, for sure. We have to see. But it's on the right track for sure.
Absolutely. Yeah.
So if you want to learn about that, if you want to understand where did life come from, how do we get from something that's not alive to alive? I mean, those are things that we need to figure out. There's a lot of work to do.
A lot of work
in
to
science.
do. Come join us.
And there's a lot of work to write about this stuff. too.
Absolutely.
So the arts are extremely important to get people motivated, to make us human.
And we need philosophy and history to show us why it's a bad idea to experiment with left chiral right life.
Right, the mirror life. What makes us human?
Right.
All of the wonderful things that we can achieve.
There we go.
Now, our next podcast will be next week. That's March the 24th. Both Robert and I will be here.
Yep.
No breaks coming up.
No breaks coming
And we
up.
have a very special guest, by the way, coming up on April the 7th. A very special guest
Yes.
from Harvard University. So Robert and I are very excited for this
Indeed.
and can't wait. So we'll say more about it as we get closer, of course. But we always leave you with a quote at the end of our podcast. And fittingly, today's quote is from
Robert Goddard?
Robert Goddard.
There we
Good
go.
man, Robert. And it is, St. Patrick's Day, right?
There you go.
So this quote from Robert Goddard then is, so I'll read it now. How many more years I shall be able to work on the problem I do not know. I hope as long as I live. There can be no thought of finishing, for aiming at the stars, both literally and figuratively, is a problem to occupy generations. So that no matter how much progress one makes, there is always the thrill of just beginning.
Nice. That is a good one.
And with
I like
that,
that.
thank you for watching today.
Thanks, folks.
Please remember to give us a thumbs up, subscribe if you haven't subscribed, and we'll see you next time.
Later on, folks.